Hello to everyone. Today I will be discussing the observed intensity distribution, that is the vibrational, in a band system, electronic band system. That is the Frank-Condon principle. So the distribution of the energy among the bands of an electronic band system varies greatly from molecule to molecule and also from band system to the band system. So once we are going from the one band to the another band, then this intensity variation are changing for all the molecules. So the typical intensity distribution for the three molecules I have shown. This is the O2 molecule, this is CO, and this I2. If you look at in this case, so the transition is taking place that once this intensity of these lines at 0, 0, it is very high, then gradually decreasing. On the other hand, in the case of the CO, the rapidly initially it is increasing, then it is rapidly, then gradually it is decreasing. In the case of this my I2 molecule, the intensities are very small and they are very high as for the continuous one, that is towards my dissociation energies. So the intensity rises gradually and the maximum reaches at the very high. This new single prime value, sometimes they continuous. That is, this is a new prime progression. These are the new progression because this 0 and this 0, 0 to 1, so 0 to 0, 0 to 1, 0 to 2. These are the progressions. New not progression means the 0 state to the high energy states, vibrational states. So the different types of the intensity distribution are explained by the Frank-Condon principle, whose basic semi-classical ideas is that an electronic transition in a molecule takes place so rapidly as compared to the vibrational motion of the nuclei that the instantaneous internuclear distance and the velocity of the nuclei can be considered remaining unchanged during the electronic transitions. Means that if the molecule is vibrating, these atoms are vibrating, so before their main position in changing, that the electronic transition is taking place. So what we could say that it means that in a potential energy curve, the two electronic states, the transition must be represented by the vertical lines. We'll see that in another next class. I'll be showing that the energy diagrams for the low energy states and high energy states. Then how vertically we are showing that these electronic transitions are taking place for the vertical axis. Then then vertically it is transition. Now in this figure, this is a potential one. This is the RE distance, at the equilibrium is distance of the atom, corresponding to nu is equal to 0. This is a wave function, that is a density function, probability density function. So the different probability density functions are plotted corresponding to nu is equal to 0, nu is equal to 1, nu is equal to 2, and nu is equal to 3. 1, 0, 1, 2, and 3. The first thing is that the electronic transitions are taking place we can show in a vertical line, and means that the electronic transition will be happening for the same internuclear distances. Means the vertical line means once I will plot an axis in this way. This is a RE. If you remember, then you have a slightly shifted. Now this transition is taking place. Whatever the state over here, either it's a 0, 1, 2, 3 for another case, this is suppose, then you have this transition for the vertical. Another thing is that the distribution of the probability density varies variational level as each electronic state. So this psi of nu mod square is varying for the different electronic states. So in this graph, in this figure, the psi nu naught square, mod square, along the various vibrational levels of the ground electron state, typical diatomic molecule. Now the greater the value of mod psi nu square at a particular value of internuclear distance r in a vibrational level, the greater the likelihood to the nuclei to found to be a distance apart. So if you look at greater the value of this one means that you have the separation between these atoms are much higher as compared to, in this case, you have psi square is just a one loop. In this case, this is a minimum. So the maximum at a midpoint of the new square. If you look at the value of the psi square is changing for the each vibration level. At nu is equal to 0, the probability or this new probability distribution new psi of nu mod square is maximum for r nu is equal to 0. However, for the other values, you have these higher values at the turning point. These are the turning points for the harmonic of this. What we define is a harmonic oscillator potential. These are the turning points. It is not a very symmetric parabolic. It is an asymmetric one. Now for this one, the value of psi mod of psi nu square is higher as its turning points. In the case of the nu is equal to 0, you have only one hump, so you have a maximum value is at the mid. So then you have the transition are taking place from here. Those transitions are more probable when they begin from or end at the midpoint of nu square. Nu is equal to 0. So the most transitions are probable once they are happening, they are transition from the nu is equal to 0 at the midpoint. Or either the turning points corresponding to nu is equal to 1, 2, 3 and so on. So you have this value of psi of nu mod square is higher for this nu is equal to 0 than the transition taking place from the center. For the higher values of this nu is equal to 1, 2, 3 and they are from the turning point. The transitions are taking place from these turning points, any one of the turning points, because you have the value of psi nu mod square is higher as the turning points. So this idea of this semi-classical idea of this Frank-Condon principle, we can state that the most probable vibrational transitions are those in which one of the two turning points of the vibrational level of an electronic state lies at approximately same internuclear distances. So we'll be plotting in the next class. If I have a same kind of the distribution over here as well, we'll see that the transition is taking place vertically from these turning points. Whatever the state over there, it may be this intermolecular distance. Suppose you have an intermolecular distance, you may have, if the transition is taking place from here, you may have a here nu is equal to maybe 2 and 3, because you must have the same internuclear distance. That is a vertical transition. And for the corresponding to nu is equal to 0, the transition most probably from this center one, because the maximum value of this psi of nu mod square. However, for the higher values, you have these turning points. So electronic state lies at approximately the same internuclear distance as one of the two turning points of the level of another electronic state, except in the case of nu is equal to 0 level, for which the midpoint rather than the turning point must be substituted. So we will see that the transitions are taking place for the same internuclear distances from the turning point, except from the midpoint of this nu corresponding to nu is equal to 0. So this is just this is how the intensity distribution, how this Frank-Condon principle defines that the intensity of this vibrational band spectra. And two things. First thing is that it has to be transitions taking place for the same internuclear distance. Same internuclear distance means the transitions for the vertical line, which can be represented with the help of the vertical line. And except this nu is equal to 0, the transitions are taking place from the turning points, because at the turning points the value of the psi of nu mod square is higher. In the case of nu is equal to 0, the value of this probability distribution is at a midpoint, then it is taking place from this midpoint again for the same intermolecular distance. We will see that in this case we will be having that for the excited state and the ground state, this RE is almost same. Then the transitions taking place, the intense light from 0 to 0, then we have a 0 to 0. On the other hand, we will see that the transitions taking place for the 0 to 0 will be slightly lesser, because the intermolecular distances are different for this molecule. Then in this case, and entirely this separation between this huge separation between the internuclear distance for the I2 molecule in a ground state electron state and the excited electron state, it's huge, and these transitions are very small, and gradually once you are increasing towards the my dissociation energy, that is continuous spectra, will be getting the high intensity light. So this is all about the Frank-Condon principle. Then tomorrow I'll be, or in the next class, I'll be discussing quantum mechanical formulation of the Frank-Condon principle. Then we'll have the intensity distribution, then for the absorption. In the emission case, then the absorption case, we'll be discussing that. In a couple of the classes, we'll be completing our molecular spectroscopy part. Thank you.